This video is recorded to help my students to understand how to prove by contradiction. A proof by contradiction starts by showing that the theorem is false, and then show that some logical inconsistencies arise as a result of this assumption. So let's use two examples to demonstrate this idea. Example 1. Show that there is no smallest integer. So if then you can say assume there is a smallest integer. Then you try to, based on that, deduct a contradiction. Okay, so let's say assume that n is the smallest integer. Okay, then let k equal n minus 1. Now we know if n is an integer, n minus 1, integer minus integer is supposed to still integer, right? So k is another integer that is less than n. How do you know it's less than n? Because it's k is n minus 1. So that is a contradiction that to the assumption that n is the smallest integer. This is contradict to the assumption that n is the smallest integer. So we started by assume that there is a smallest integer. Okay, then we conclude a contradiction because you assume n is the smallest integer, but you found another one even smaller. That means your assumption can never be true, right? So that's proof that there is no smallest integer. Okay. Now, second one. Second one says, show that square root of 3 is irrational. So to prove this, we can assume that square root of 3 is rational. Now, you need to understand the definition of rational. A definition of rational, which means a rational number is a number can write as P over Q, where PQ are integers and they have no common divisor. So, which means you can write it as a reduced fraction form. Okay? So we need to review what is the definition of rational, which is a number can be written in reduced fraction form. For instance, 2 is rational since 2 equal 2 over 1, right? You can write a reduced form, okay? Now, 1.25 is rational since 1.25 you can write it as 5 over 4, which is a reduced fraction form, okay? So anything you can write as reduced fraction form, that is a rational number. So now in this case, if you assume square root of 3 is rational, which means that is you can write square root of 3 equal P over Q, where the GCD of PQ equal 1. Okay, that means PQ is a reduced form. Okay, so if this is true, then let's see if we can conduct some contradiction. So since you have square root of 3 equal P over Q, what that mean? That will give you P equal square root of 3 multiplied Q, right? Because you multiply Q both sides. Then you square both sides, then you will have 3 Q square will equal P square. 3Q square is a square. Q square will equal P square. Now, notice P and Q, there is no common factor between Q and P and Q. But since the left side is a multiple of 3, okay, then the right side must be a multiple of 3. Okay, so P square must be a multiple of 3. then P must be multiple of 3. If P squared is a multiple of 3, then P must be a multiple of 3. Now, this one, we can prove it later. But at this point, we accept this fact. If P squared is a multiple of 3, then P must be a multiple of 3. Now, if P is a multiple of 3, that is P will equal some 3m for some integer m. Because it's a multiple of 3, right? So it's 3 times some other integer. Okay? So you replace P equals 3m into this, then we can say what? 3q squared equal P equals 3m. Okay? So that is 3m squared, which is 9m squared. Okay? Now, then you divide 3 both sides, that is q squared will equal 3m squared. Okay? So, since you divide 3 both sides, right? Now, we conclude, so q squared is a multiple of 3. That is q will equal 3n for some integer n. Now, notice P is a multiple of 3, and Q is a multiple of 3. So the greatest common divisor of P and Q at least is 3, because they both have 3 as a factor, right? So GCD of PQ at least is 3. Or you can say 3 is a factor, common factor of P and Q, which is contradict to GCD of PQ equal 1, because you assume PQ, they have no common factor. Oh, here I miss Q here somehow. Okay, the GCD of PQ is 1, because you assume square root of 3 is a rational number, which you can write in the reduced fraction form P over Q. Since it's reduced form, that means PQ's greatest common divisor is 1. Okay, now based on this assumption, we do it step by step. We found P will be a multiple of 3 and Q will be multiple of 3. That means the greatest common divisor of P and Q at least is 3, because 3 is the common divisor factor. So that's contradicted to the assumption that the GCD of PQ equal 1. Okay, since your assumption is wrong, right? If you assume is a rational number, you get a contradiction. That means your assumption is wrong. So that means square root of 3 is irrational. Okay, so the only thing left over is we need a proof that if P squared is a multiple of 3, then now let's prove that if P squared is a multiple of 3, then P must be a multiple of 3. Now, you can prove this by what? By contradiction. Okay? Now, if P is not a multiple of 3, then you prove P squared will not be a multiple of 3. Okay? So, the way to prove, suppose that P is not a multiple of 3. You prove it by contrapositive one. Suppose P is not a multiple of 3, then P squared is not a multiple of 3. This is proof by contrapositive. Okay? Now, if P is not a multiple for 3, then P equal what? Let P P is well, let's say this way. You divide it into cases. Even you want to prove this contrapositive, you divide in cases. Since P is not a multiple of 3, you have two cases. P divided by 3, remainder is 1, or P divided by 3, remainder is 2. Okay? So, case 1, P, let's put it this way. P equal 1 mod 3. That means P divided by 3, remainder is 1. I.e., that is P equal 3m plus 1 for some integer m, because he divided by 3, remainder is 1. Then P square equal 3m plus 1 square. Okay, that will give you 9m square plus 6m plus 1. Okay, that will be 3 times 3m square plus 2m plus 1. Now notice the first portion is 3 times an integer. That means a multiple of 3. Multiple of 3 plus 1 is not a multiple of 3, right? Which is not multiple of 3. Okay, case 2. I just copy and paste this, then I just change accordingly. Case 2, which is P divided by 3, the remainder is 2. Then your P will equal some 3m plus 2, right? For some integer m. Then P square is 3m plus 2 square, which is 9m square plus 12m plus 4. Okay? So then you take a 3 factor out, use 3m square plus 4m plus 1, then plus 1. Now, notice the first portion is a multiple of 3. Multiple of 3 plus 1 is not a multiple of 3. So in either case, you proved if P is not a multiple of 3, then P square is not a multiple of 3. Then proof by contrapositive, which means if P square is a multiple of 3, then P must be a multiple of 3, right? So those we finish the proof. If you have any questions, please give me an email.